Hello again, physicists. Today, I have a tremendous topic for you. Newton's three laws, specifically laws of motion. These will become the foundation for a lot of what we discuss throughout the year. It's important that in addition to anything that you see during this video, you also make notes that kind of paraphrase what I'm explaining, because it's just essential. It really is for this particular topic. The more detail you can get out of your video today, the better. So with that said, let us begin, starting with Newton's first law. This is sometimes referred to as the law of inertia. It basically says that objects have a tendency to resist a change in their state of motion. That means that if an object is at rest or moving at a constant velocity, it does not want anything to change about that scenario. That object wants to continue staying at rest, or it wants to continue moving at that same velocity. And the only way to change that state of motion will be to have some sort of net force acting on the object. So here I have a scenario where we have a little clip from The Simpsons, and Homer Simpson is filling in for Krusty the Clown, and he is driving the Krusty Mobile, and some hilarity ensues. So let's take a look at what happens. So he's driving, going to a kid's birthday party, and then crunch. Boom. And he's not feeling so well. So there you go. This is actually a good demonstration of Newton's first law, because as the car is driving, both Homer and the vehicle are sharing the same motion. They're moving at a constant velocity until the car hits the tree. At that point, something has changed about the state of motion for the tree because it experienced a force, the tree hitting it. Homer, however, his state of motion is not changing because he did not have a force exerted on him. The tree didn't hit him, it only hit the car. And it's because of that Homer went through the windshield. He was moving at a velocity. The car itself decelerated. Homer did not. And therefore his state of motion continued, and that's why he was thrown through the windshield here. So there's a demonstration of Newton's first law of motion. We've already kind of discussed Newton's second law of motion in class, and that was the relationship between acceleration, a net force, and the mass of a system. So basically, the change in state of motion for a system will depend on the mass of that system and the magnitude of the net force acting on the system. And that leads to this equation right here, where A is the acceleration of the system, F net is the net force acting on the system, and m is the mass of the system. Essentially, if we have a constant mass for the system being held, and then have an increase in the net force, it means that the acceleration will also increase. We can also say that if we hold a constant net force on the system and have an increase in mass, the acceleration will, as a result, decrease. And that's essentially all that Newton's second law can tell us. It's a very versatile formula. We will use it many ways throughout the course to find several unknown quantities. So get used to this equation. It will be our bread and butter in our current unit, and it will show up in other places in other units. The last law, Newton's third law, sometimes called the action-reaction law. This is one that a lot of students have misconceptions on. It's saying that forces will occur in action-reaction pairs. In other words, if I have two objects, and object 1 exerts a force on object 2, it means that object 2 will then exert a force back on object 1 that is equal in magnitude and opposite in direction. It is important to know that when you are drawing a free body diagram for a system, You should never have both the action and reaction forces present on that free body diagram. Question is, why? Well, free body diagrams, keep in mind, they are only for the forces that are being exerted on the system. So if you have an action force acting on your system, the reaction force is actually exerted by that system. And those are forces that we do not draw on our free body diagram. So here's an example. Let's say we have an astronaut floating above the Earth, and the astronaut, just the astronaut, will be our system. If I drew a free body diagram for the astronaut, well, he'd only really have one force acting on him, and that is the force of gravity caused by the Earth. So here, the action force would be the Earth pulling on astronaut. Now, what would be the reaction force? The easiest way to think about reaction forces as opposed to action forces is that it has to involve the same two objects, and it's just going to be the same action reversed. So in this case, the action was Earth pulling on the astronaut. The reaction force will be the astronaut pulling on the Earth. And in our free body diagram, that does not show up because, again, I don't draw in forces that my system is exerting. I'm drawing in forces that are exerted on the system. I don't draw anything that the astronaut's doing in terms of how he's influencing his surroundings. It's only what the surroundings are doing to the astronaut that actually shows up here. And this holds true throughout. If there's ever a case where you have both the action and reaction forces drawn on your free body diagram, it basically means that those are internal forces to your system, and they shouldn't even be there in the first place. So there you go. So here's a little trivia for you. I have a block resting on a flat surface. The block has mass m, and I am exerting a force using my finger that is pushing down on the block. The question is, what will the reaction force be? So here is my action force. What will my reaction force be? Will it be A, the table pushing up on the block, B, the block pushing up on me, or C, the block pushing down on the table? Pause, take a moment to think about it, and then we'll see what the answer is. The answer to our question, what is the reaction force to me pushing down on the block? The answer is the block pushing up on me. So it would be choice B. Choice A would not work because this is an interaction involving not the same two objects. Keep in mind the action force was between me pushing down on the block. Choice A is an interaction between the block and the table, not between the block and me, therefore making it incorrect. Choice C is also involving an interaction between the block and the table, not the block and me, therefore it is not correct as well. Only choice B has an interaction that describes something occurring between the block and myself, therefore making it the correct choice. Keep in mind that this reaction force would be equal in magnitude, so it would be equal to whatever force I was pushing down on the block with, and it would be opposite in direction. So if I wanted to draw in that reaction force, it would be pointing up back at me, and it would have also a magnitude of F. So action, me pushing on block, reaction, block pushing up on me. That's all I have for you today, physicists. Tomorrow we will spend a lot of time actually looking at problems related to Newton's 3 laws of motion. So until next time.